Last night, the X platform, formerly known as Twitter, saw a huge influx of traffic, which caused a lot of people not to be able to use the platform and not access a lot of the services. People call this a distributed denial of service attack, or DDoS. Elon Musk even called it this. But I do think it's a really fascinating case of, is it a DDoS attack by malicious attackers, or was it just a lot of people sort of making the platform go viral, trying to access the service? If you didn't know, last night Elon Musk was going to interview Donald Trump on the platform on the X Spaces. We're not even going to get into that. We're only going to look at the technical details, and I want to look at a deep dive on what DDoS attacks are, how you can detect them, and specifically how you can detect them compared to just normal influx of traffic, how you can prevent them, and how you can recover from them. So let's take a look. So this is much of the context for this whole thing. Last night there was the interview that they were going to do on Spaces. Elon claims that it was a DDoS attack on X by malicious actors, but from The Verge, they were told by X insiders that it was not. And I do think that this is really fascinating. It can actually be very, very difficult to tell the difference between a denial of service attack from a malicious actor versus just your platform going viral and getting a massive influx of traffic. So let's look at what exactly a denial of service attack is. So DDoS, this stands for distributed denial of service. This is slightly different than just a normal denial of service. Denial of service would be if you had one computer sending many requests, essentially all from the same IP. You used to be able to do this like way back in the 90s and the early 2000s, where if you just constantly refreshed a website, in theory you could bring it down, just because people weren't scaling resources at that time. There wasn't a lot of IP banning or on the edge type of traffic restrictions, but these days preventing a normal denial of service attack is almost trivial. You just look for that single IP and you rate limit based on that single IP. About that simple. So the solution on normal denial of service attacks is to rate limit. So a distributed denial of service attack is that same concept where you have computers, but many different distributed computers hitting a service, hitting a website, hitting something all at once, causing essentially those services and those resources to be completely exhausted, denying access to that service by other people, by normal people. So we can look at this like this. If I have this is my service here. It's just running maybe on a single box, on a single container or something. And if I have many thousands of other computers all at once accessing this resource, maybe my network traffic graph all of a sudden looks like this, and we just have a huge influx of traffic all of a sudden. That would sort of be like a distributed denial of service attack. But the very important thing to remember here is that this sudden influx of traffic, this could be a viral moment. So this sudden uptick could maybe be, your website going on Hacker News, going viral on Twitter, Threads, Instagram, whatever. That looks very similar to a distributed denial of service attack. And that's what really, I think, happened last night, is that really, these many computers accessing the X service all at once were not malicious actors, taking over computers and hitting the X service all at once. It really was just normal people trying to get on the platform to get into the space. One of probably the most important things to remember about distributed denial of service attacks is that oftentimes these malicious actors have computers that they've taken over or that have these viruses or malware on them that allow them to do these distributed denial of service attacks. Oftentimes they have those computers in similar geographical locations, which usually means that those computers will be on the same IP ranges. So in this example here, all of these computers that are all hitting this service at once might have the same IP range. Maybe it's something like, 19, 18, 17, and it goes all the way from 0 to 25. Maybe that's like the range of IPs that have been assigned to all these computers. because they all exist somewhere in Russia is a really good example. So if you're all of a sudden seeing this huge spike in traffic, here's our graph again, normal traffic, huge spike, things are going crazy, and you notice that this huge spike has all of these IP ranges all originating in Russia, then you can be pretty certain at that point that it's probably a denial of service attack of some kind. For really huge platforms, it's very important that you have a good understanding of normal geographical usage, and you can sort of map that over time to understand the patterns that happen within given amounts of time. Once you have that data, you can even get pretty fancy and apply machine learning, anomaly detection to that data to determine if different regions are having unusual spikes of traffic that may indicate the start of some malicious and abnormal traffic. So there's so many different ways of doing this, but each of those is going to represent, the traffic over time for a given region. So maybe this top one is the United States, where typical traffic, spikes in the morning and then teeters off, and then by the middle of the night is, not very much. Maybe in the European Union, it's a little more something like this, where it spikes up in the middle of the night for the United States. And maybe in, Asia regions or something, it looks even slightly different, where it's kind of spiked and then it comes up and then like this, where you can sort of get an idea over a period of time where, the middle of the night is. So this would be, for our example, this would be the middle of the night for, this Asia region, for example. Now, if we saw a chart that all of a sudden, let's take, the United States, for example, where, things are maybe looking sort of normal in the middle of the night, and then all of a sudden there's a huge spike, and then it just kind of drops off, and then we see normal-ish traffic. This would 100% be an anomaly that doesn't make sense in any kind of normal traffic patterns. This would be a complete anomaly that you could start to build some understanding of maybe what a malicious attacker is doing. Because oftentimes what you see with these types of attacks is they'll try a little something, they'll do a little blip here or there before they really unleash a big attack. It's really a big game of cat and mouse in the end. So you want to have the monitoring and observability infrastructure to be able to look at stuff like this, be able to detect anomalies, and then be able to respond accordingly. There's a number of other things that you can start to look for, even little things that specific cloud services can really help you with, like Cloudflare and all those things. Those specific tools have specific opinions about preventing DDoS attacks and detecting them. Different things about analyzing, user requests, looking at the actual user agent strings that are coming in from your requests, analyzing those patterns and those geographic locations and IP ranges even deeper than you might be able to. Definitely recommend using one of those specialized services, especially for hyperscale platforms. So now the question becomes, what is really the true difference between a viral moment and maybe a malicious denial of service attack? And I think that's really what's interesting about this situation with X and, the huge scale that they saw with the space last night. So the real big difference ends up being traffic source diversity. So again, if we look at the number of graphs maybe that they would have, I'd imagine that if they had some kind of graph that was a distribution or maybe a histogram of different IP ranges or even region based, they would see rather steady sort of distribution among all the different traffic sources trying to access the space last night. For a true distributed denial of service attack, what you would see is, pretty distributed, consistent across the board kind of different ranges. And all of a sudden you would see a spike in maybe like, this is a very specific IP range. And then maybe it goes down, maybe you'd see that spike again. Again, very specific IP range or region specifically. And you could put this, into a histogram. There's 1,000 different ways to spin this with the data. But the important thing here is that you'd want to be able to somehow detect the diversity of the actual traffic. Now, the one thing I will say is this is a very, very hard problem to solve, especially for extremely sophisticated distributed denial of service attacks, because it would not be that hard, given enough resources or maybe nation state backed resources to just have a botnet of distributed computers all over the globe with a wide range and variety of IPs within different regions to really subvert many of these different kinds of detections that we've talked about here, even really sophisticated detections using some of these cloud platforms and cloud services out there. So this is a very hard problem to solve. Differentiating beyond, the simple like, oh, is it a variety of different kinds of traffic? What's the diversity like? What's the traffic quality look like? Are the agent headers different? Are the packets actually, well formed? Is it using the right IP version? All that kind of stuff. Beyond that, it does start to become an extremely difficult problem. So at that point, from an infrastructure standpoint at least, it really becomes a question of recovery and prevention. Recovery and prevention. So if it's such a hard problem at times to detect these mass scale distributed denial of service attacks, instead, what you can do is have infrastructure and automated tooling in place to ensure that the platform is still up and healthy and able to recover at hyperscale when needed. And all throughout the scale, you can have these sort of auto-scaling and automation pieces of tooling that can really help harden the platform in these cases. Everything from, the bare bones compute that you could auto-scale from being, hard-coded instances to auto-scale out to any number of instances you might need as traffic is coming in. Things within the network. I guess that kind of looks like a basketball, but that should be the global internet icon. Your network can even auto-scale, giving you more ranges of IPs that you might need allocated to these compute instances, or with bandwidth that might come in and out. Same thing can be said for firewalls around your networks. Firewalls and all that is often a missed part of this, which really maybe kind of dips into the more DevOps, IT, cloud solution side of things. But really good firewall solutions can oftentimes just at the network layer prevent these kind of really nasty denial of service attacks with rate limiting, single IP banning, that kind of thing. Let's look at a slightly more in-depth example on how you would do this with, something maybe I would design from scratch. So maybe in a very arbitrary case, there's something that is, a bit of compute. Maybe this is just an API. Maybe somewhere there is a database. Let's call this database. And maybe there's some front-end client that's serving, some client of some kind. So a client is obviously going to hit the API. The API is going to need data from the database, and the API returns that back to the client. Now, this is fine, but obviously would be very, very susceptible to any kind of denial of service attack, even really arbitrary ones from a single client just hitting refresh over and over and over again. So as clients would scale, and as you would maybe need to start preventing the threat of denial of service attacks, you would want to obviously auto-scale your API over here. And maybe a solution you would use is something like Kubernetes. That'd be my solution of choice, but dealer's choice with this. But then you would also want to auto-scale resources on your database as well. A quick note on the cost over here. This can often be a piece of what a denial of service attack from a malicious actor is about, is not only draining your compute resources, but also your financial resources. It's easy for me to sit here and say, ooh, just auto scale all this stuff. But, to small companies or even medium-sized large companies, getting unfettered auto scaling all of a sudden, you go from maybe 5 of these instances times that by 100, you need to 100x your scale just to meet the demand of traffic up to 500. You've essentially 100x'd the cost of compute here alone. And if one of these instances is, $1,000 a month, which isn't obscene, but is a little expensive, you've essentially 100x'd that $1,000 a month. And maybe that was the goal of the malicious actor all along, was, to see if they could just drain a bunch of resources off of whatever company, whatever service is being used. So I don't want to forget this part. The money side of this is totally a thing. But you can even set limits on a lot of these auto scalings. A lot of the platforms out there that offer these set the limits, like set limits so that you're not just going to be like totally drained in the bank, draining all those resources from some kind of attack as well. Okay, so we've scaled up our API. We also want to scale up the database with resources, CPU, memory, and a bunch of different things depending on your database of choice. Maybe it's a connection pool. Maybe it's a read-write replica. There's a ton of different choices for really good distributed and highly scalable data solutions. Once you're in your ecosystem, be it Postgres, SQL, whatever, there are good solutions out there for that. Now, I would say that this is fine, maybe still arbitrary. We had mentioned a firewall, and there's a few things that I would do in this layer right here, really between the client and the API itself. The first thing that I would do in this layer is really probably do a CDN is maybe the obvious choice. That's a content delivery network. And that's really where your API, your data, it can serve content distributed globally at a high scale without always having to hit your API. It just distributes that content if it's appropriate content from your service to the CDN, things like images, newly created client resources. So maybe Instagram, for example, somebody posts an image. Maybe that first lands in the CDN so that the CDN can just serve that directly back to clients that are within that region for that CDN without having to round trip it back to the API, down to the database, back up to the API, et cetera, et cetera. So yeah, CDNs are really great and really, really useful. The next thing that you would really want is firewall. Firewall, as I mentioned, depending on your network configuration, that can just give you a bunch of stuff for free. Firewalls and a lot of the cloud service firewalls are very, very good for doing IP-specific banning, rate limiting, just malicious types of traffic, like irregular types of traffic with like junky, poorly formatted packets. Firewalls can just prevent that and give you like a ton of security out the gate. So maybe those two are obvious, but CDN, firewall. I would probably also implement my own rate limiting at this layer as well. And that sort of dips over a little bit into the API side. But you can have custom rate limiting configurations at the client API, really that first layer here. Another really good one to mention here, obviously, a load balancer. Specific clients within specific ranges, depending on, your firewall configuration, your CDN, this whole kind of network trafficking piping into the API. You don't want them just hitting one of these. So, maybe this one back here, maybe I have some client here and misconfigured all this, and it's just continuously slamming one of these over and over and over. Load balancers will ensure that traffic is distributed evenly past your network layer into your actual compute layer here, so that each of those is getting sort of an equal and shared amount of traffic, so you're not exhausting any single one unit of compute. Load balancer is very important. You get that for free, again, with a lot of platforms like Kubernetes. The Kubernetes load balancer is very good. It works great. You can even extend that to be a little more advanced with advanced types of rules and all different kinds of things. I mentioned this briefly before, but a really, really important part of hyperscale for any platform, really scale of any kind for any platform, is monitoring and observability of all of this. So we'll call this M and O for monitoring and observability. You have to have good monitoring and observability practices within this whole thing, because if you can't see what's going on within your CDN, within your firewall, your load balancers, your API, even within your database, within the traffic that's happening here, within the traffic that's happening here, all of it, it becomes very, very, very difficult to actually go and troubleshoot any different piece of this that might be a bottleneck. There will be bottlenecks somewhere in your implementation or within your architecture. That's just a given. But good monitoring and observability allows you to ask the question where and how, and then allows you to sort of like a scientist would gather data, gather insights and understanding, and then go and make informed decisions to actually, fix the individual pieces based on the data you have for monitoring and observability. Getting even crazier, down here with the database, I'd maybe even consider doing some sharding to give us even more scale with the data. And maybe the last thing I would actually mention here, let's zoom out just a little bit. I would probably also think about re-architecting some of these bits and pieces to get caches and message queues. There's a few different places I think caches would make sense. Obviously, a cache on the API side, probably a cache here between the actual data and your API. That just makes sense. But also implementing some message queuing so that there's not just a huge influx at any one given time. Maybe between clients and an API, you could put between maybe your load balancer here, an MQ right there, so that your API can have a consistent level of traffic pulling stuff off of a message queue. You would then, obviously adding components to any architecture, need to scale that alongside the rest of it as well, ensuring that your message queue and your caches are resilient, and even when those would maybe fail over, that you would have fail safes so that the platform doesn't go down entirely, because caches and message queues are essentially memory based, and if those go down, if memory is completely exhausted, you need fail safes on top of that as well. And that at least is a good place to start. It's really hard to say specifically like this is what you have to do to scale and prevent these kind of attacks, or prevent mass influx of traffic. Every little application, every platform, every hyperscaling situation, honestly, is different. One resource that I would recommend, that I recommend to a lot of people, I talk about this book all the time. This is Designing Data Intensive Applications. This book is so good. This is really like a masterwork in doing huge hyperscale. The subtitle is The Big Ideas Behind Reliable, Scalable, and Maintainable Systems. And in the end, that's really what anybody running a platform is trying to achieve. Denial of service attack or not, just hyperscale in general. In the case of X, I would not say that it was a denial of service attack. I would just call it a hyperscaling situation where, they had a huge influx of traffic. Bits and pieces probably fell over, which caused the whole system to fall over and become inaccessible to people. I hope you liked this video. Let me know what you think. Give me a like, comment, subscribe, all those things. It really helps out the channel. And I will catch you all next time. All right, peace.